Okay, today we're going to do topic 8.13, arc length of a smooth planar curve and distance traveled, AP Calculus curriculum. Learn objective is determine the length of the curve in the plane defined by a function using a definite integral. We're going to start by looking at the geometry behind finding arc length using definite integrals. We're going to start looking at a function, just an arbitrary function, graphed in the plane. And we want to find the arc length. If a particle was traveling along this path, we would want to find the arc length from A to B along that path. Let's look at this. We can blow it up some. So what I want to think about here is if we were to measure that arc length, we would be looking at this part of the curve. Now, what I'm going to do is take a piece of that and make it larger so that we can give you an idea of what's going to happen here. Because effectively what we're doing is we're looking at very small pieces of that curve. And even smaller than this, infinitesimally small little pieces of the curve is what we want to break this into. Little small pieces. If we could make those infinitesimally small and add them all together, we would get the length of that curve. And so what I want to do is now take out one of these little pieces. We're going to call this one piece ds, or the change in arc length. If s is the total arc length, then ds is the infinitesimal small change. We can consider ds in relation to y or x. We're going to use ds in relation to x most of the time, but it's the change in the arc length. And if we could sum all those ds's, we'll have ds of n. We could take the limit as ds goes to 0, becomes infinitesimally small, and we would have the arc length. But that's just the integral from a to b of those ds's. So what is ds? We're going to take this one little piece out and we're going to amplify. If we were looking at that here, we might call it small piece right here. And notice that as that thing gets really, really small, what we can look at is this is just basically the line between 2 points on the graph, where this distance, horizontal distance, is the change in x, and the vertical distance is the change in y, and it forms a right triangle. And if this is ds, then by the Pythagorean theorem, we have ds equals the square root of dx squared plus dy squared. So that if we sum from a to b all the ds's, what we're really summing is the square root of the sum of the squared differentials. Now what's really cool here is that we can factor out a dx inside there, or dx squared, and say that this is going to be dx squared times 1 plus dy squared, dy over dx squared. And that is the integral from a to b of the sum of 1 plus dy dx all squared times dx. And this is something we can integrate. And when we integrate it, it's going to give us the arc length of the curve. So let's look at this again on our OneNote. And we've just established that the arc length S, as we go from A to B on some curve, is equal to the integral of A to B of ds, changes in the arc length, which is the same as the integral from A to B of the square root of 1 plus dy over dx all squared times dx. So if we can integrate that function, we can get the arc length. Let's try this with a really, really, really simple curve, one that we really don't even need this for. Let's use the line y equals x, and let's just go from the origin to the point 2, 2. Now we know, using the Pythagorean theorem, that this is 2 squared plus 2 squared. Oops. It's 2 units, and that's 2 units, and that's a right triangle. So that we could say that S from 0, 0 to 2, 2 of this curve, y equals x, is the square root of 2 squared plus 2 squared, which equals the square root of 8. But let's try it using this integral formula. We can say that S is equal to the integral from 0 to 2 of the square root of 1 plus, now dy dx for the line y equals x is just 1. So this is going to be 1 squared times dx, which is equal to integral from 0 to 2 of the square root of 2 times dx, which is equal to integral from 0 to 2 of the square root of 2 times, this is a little carried away on my integrals there. This is equal to the square root of 2 times x evaluated from 0 to 2, which is 2 square roots of 2 minus 0 square roots of 2, or just 2 square roots of 2. And since the square root of 8 is the square root of 4 times 2, 4 comes out, becomes 2 square roots of 2. So that's just a real simple linear example. We didn't need the integral for to calculate the arc length, but to show you that it works on that. We'll do some more examples in the next few videos. That's just the geometry behind finding the arc length. The formula for finding the arc length of a curve equals this. And we'll do some examples in the next videos.